Welcome to Slice of Physics. I'm going to be talking about capacitors and capacitance. So you've already learned about capacitors. We often draw a capacitor like this as two parallel plates, and we talk about how there's some charge on one of the plates, maybe some positive charge on one plate and some negative charge on another plate, and there's an electric field going from one plate to the other. And there's also a potential difference, and the potential lines look like that. That's a capacitor. From another side view, it would look like this. There would be some plates, and they would be close together. Maybe there would be a wire coming out of them. Often there's a wire coming and they're hooked up to a battery. That's a capacitor. So what is a capacitor good for? Well, the word capacitor sounds like the word capacity, which sounds like it must mean the capacity for doing something, for holding something perhaps. So a capacitor has the capacity to store charge. That's what a capacitor does. It stores charge. So this charge sits on the capacitor plates, and it could be used for something. What could it be used for? Well, let's take a few examples. Example 1, a camera flash. So on a camera, you sometimes want a very bright light to flash out for a short period of time, and that's going to require a current to be running through the bulb on the camera, and that current, as we'll talk about later in the course, is a flow of charges. So what we need is a very short flow of charges, and we need to store the charge to make that camera flash. So the capacitor can store that charge that's used to make the camera flash. Another example where a capacitor is needed to store charge is in a defibrillator, like the machine that's used to restart someone's heart. So the defibrillator needs to store charge, kind of like the camera flash needs it, except that instead of running that current through a bulb, it's going to run that the current through a person's body, through their heart, in order to restart their heart. And you need a gigantic capacitor to store all of that charge that's going to be flashed through the person. Another example is let's say you have to change a battery on some little electronic device. And this electronic device, let's say the device wants to retain some of its memory while you're taking the battery out. So it needs to store some energy while you remove the battery. So where will it store that energy? One place it could store that energy is a capacitor. So it might just be able to store enough energy to keep operating for a few seconds while you change the battery on a capacitor. So if capacitors are good at storing energy, then you might ask how much energy can they store, or if they're good at storing charge. In this case, they're for storing charge. In this case, they're for storing energy. So we might ask how much charge can they store and how much energy can they store. So let's start with the question of how much charge they can store. Alright, so I'm going to have a capacitor here, and I'm going to hook it up to a battery. This wire will go to a battery, and that will connect here. And let's say this battery provides 5 volts. So that means delta V across the capacitor is 5 volts. So now I might want to know how much charge this capacitor can store. What is Q? Well, it certainly seems as though the bigger the battery, the more charge it can store, because as I put a bigger and bigger battery, more and more pluses will align on this plate and more minuses on this plate. In fact, if I double the size of the battery, the voltage of the battery, then twice as much charge will be stored on the plate. So it seems as though there might be this ratio, charge per volt, that can be stored. If I double the charge, then I double the volts. If I double the volts, then I double the charge. And this ratio is called C for capacitance. So that is the capacitance. And it tells you how much charge the capacitor can store for each volt that is placed on it. So a 5-volt battery could store 5 volts worth of charge. Okay. So now let's do a calculation to find out how much charge can be stored on a capacitor, given some basic information about it, like its area. So we know that in a capacitor there's an electric field, and we know the formula for the electric field is the charge on one of the plates divided by epsilon naught, which is a constant, times A, the area of the plates. And we also know that the delta V across the plates is equal to E delta X, where this is the width of the capacitor. And that means that delta V equals Q delta X over epsilon naught A. So now we want to know how much charge can be stored. Well, we just have to rearrange this equation, and we get that charge equals epsilon naught A delta V over delta X. And that means that the capacitance, which is the charge divided by the potential difference, we have to divide out the delta V. Let me do that up here. So up here I'll put C equals Q over potential difference equals epsilon naught A delta V over delta X. That's the Q. And then I'm dividing out the potential difference, so, and I get that the capacitance equals epsilon naught A over delta X. So that is the amount of charge per volt that can be stored on the capacitor. So what this tells you is, if I put a volt of potential difference across it, if I put a 1-volt battery across it, how much charge will be stored in coulombs? So it's important to realize that capacitors can have any shape you can imagine. So I could imagine a capacitor that is made of 2 spheres, and maybe the plus charges come on this sphere and the minus charges come on this sphere. So in that case, we know that these spheres are conductors, and so they are equipotential surfaces, meaning that every point on this conductor has the same potential. As there is one potential on this conductor, we'll call it V1. And on this conductor, there's another potential, V2. And there's a potential difference, delta V equals V2 minus V1. And there's also an electric field, just like always. Right? And so the point is, there's still a capacitance. Capacitance is just defined as the charge on one of the spheres, and of course the negative amount of that charge will be on the other sphere, divided by potential difference is the capacitance. Now, there may not be a nice formula for it. So with these two spheres, it's not the same formula for the capacitance as it was before, but it does have some capacitance. And if we double the amount of potential difference, then it will double the amount of charge that's stored on the capacitor. Okay. So in this lesson we learned about capacitance, what it is, that it's the charge divided by the potential difference of a capacitor. And we learned the formula for the capacitance of a parallel plate capacitor. And we learned that capacitors can have different shapes, and that all capacitors have a capacitance, even if we don't know the formula for that capacitance.